The object now being referred to as 3I Atlas wasn't supposed to exist in the first place, not because it violates a single law of physics, but because it quietly breaks several expectations scientists have relied on for decades. When it first appeared in survey data, it didn't announce itself with a dramatic explosion or a blinding flare. Instead, it slipped into view like a rounding error that refused to go away. At first glance, it looked like just another fast-moving interstellar interloper. But the deeper astronomers looked, the stranger it became. To understand why 3I Atlas is unsettling, you need to understand what normally comes from outside our solar system. Interstellar objects are rare. Before 2017, we had never confirmed one at all. Then came Oumuamua, a visitor so odd that it ignited arguments still unresolved today. 2 years later, Borisov followed, a far more conventional comet that reassured scientists that interstellar visitors could be explained using familiar physics. That sense of relief didn't last long. 3I Atlas now sits in an uncomfortable middle ground between those two extremes. And that's exactly what makes it dangerous to our assumptions. The first anomaly is its trajectory. 3I Atlas is moving too fast to be gravitationally bound to the Sun, confirming its interstellar origin. That alone isn't shocking anymore. What is shocking is the precision of its path. When researchers backtracked its motion, they found that it wasn't tumbling randomly through interstellar space. Its incoming vector appears unusually clean, as if it traveled for millions of years without being significantly perturbed by stellar encounters or molecular clouds. Space between stars is not empty. Over long distances, objects tend to get nudged, slowed, or scattered. 3I Atlas seems to have avoided all of that, arriving with a trajectory that looks almost engineered by circumstance. Then there's its velocity profile. Interstellar objects usually show signs of acceleration changes as they heat up near a star, especially if they're icy. Sublimation creates jets, which act like thrusters, subtly altering motion. With Oumuamua, this non-gravitational acceleration was detected but without the usual cometary tail, triggering endless debate. With Borisov, the behavior was textbook. 3I Atlas, however, shows a weak but persistent acceleration that doesn't line up cleanly with either model. It's not behaving like a rocky asteroid. It's not behaving like a classic comet. It's doing something in between, and doing it consistently. Its brightness compounds the mystery. Based on how much light it reflects, astronomers can estimate size and surface composition, but 3I Atlas refuses to settle on a single answer. Depending on the angle and wavelength observed, it appears alternately darker than coal or oddly reflective, suggesting a surface that may be layered, textured, or coated in materials rarely seen in solar system objects. One hypothesis is that it's covered in an irradiated crust, baked by cosmic rays over millions of years, forming an insulating shell. That would explain its muted activity near the Sun. The problem is that models predict such crusts should crack or shed under solar heating. 3I Atlas hasn't done that, at least not yet. Another issue is its shape. Early light curve data suggests it may be elongated, but not to the extreme degree seen with Oumuamua. Instead, the variation hints at something irregular but stable, rotating without chaotic tumbling. That stability is strange. Interstellar space is violent on long timescales. Objects collide with dust at enormous relative speeds. They experience tidal forces when passing stars. Over millions of years, most small bodies end up spinning erratically. 3I Atlas rotates like it's been protected from that environment, or like its internal structure dampens rotational chaos far better than expected. Composition models only deepen the puzzle. Spectroscopic scans hint at compounds that don't neatly match common cometary signatures. There are weak signs of carbon-bearing molecules, but not in the ratios astronomers are used to. Water ice, if present, is strangely subdued. Some models suggest exotic ices like carbon monoxide or nitrogen dominate instead. That idea echoes one explanation for Oumuamua, proposing it was a nitrogen iceberg chipped off an exoplanet. But if that were the case here, 3I Atlas should be losing mass rapidly as it warms. Observations don't show that level of mass loss. There's also the question of timing. 3I Atlas was detected relatively early in its approach, compared to previous interstellar objects. That's partly thanks to better surveys, but it also suggests it's unusually detectable for its size. Either it's larger than initial estimates, or it reflects light in a way that makes it stand out against the background. Both possibilities are uncomfortable. Larger size implies interstellar space is littered with more big objects than models predict. Enhanced reflectivity implies unusual surface physics we don't yet understand. Some researchers have pointed out an even subtler anomaly: thermal behavior. As 3I Atlas approaches the Sun, its temperature increase doesn't perfectly match predictions. It heats more slowly than expected, as if heat isn't penetrating its interior efficiently. That supports the idea of an insulating shell, but again, such shells shouldn't be this resilient. If the object is porous, heat should seep in. If it's solid, internal stresses should build. Neither outcome fits what we're seeing. Naturally, speculation follows. Most scientists are cautious, sticking to exotic but natural explanations. They talk about rare formation environments around other stars, unusual chemical histories, or objects formed in the cold outskirts of alien planetary systems before being violently ejected. These are all plausible, and none require rewriting physics. But the uncomfortable truth is that each explanation solves one problem while worsening another. Fix the acceleration, and you break the brightness. Fix the composition, and the thermal data stops making sense. The reason 3I Atlas feels different isn't because it screams impossibility. It's because it whispers inconsistency. Every measurement is just close enough to normal to avoid dismissal, but just far enough off to resist comfort. It sits in a gray zone where models stretch thin. That's often where real discoveries happen. There's also a broader implication. If 3I Atlas is natural, then interstellar space is far more diverse than we thought. Our solar system may be a poor representative sample of what's out there. The objects we've built our theories on could be local oddities rather than universal standards. That realization would ripple through planetary science, forcing revisions in how we model planet formation, ejection processes, and the chemical evolution of galaxies. On the other hand, if future data reveals behavior that cannot be reconciled with natural processes, even after exhausting reasonable explanations, then science faces a more uncomfortable task. Not because it points to anything sensational, but because it would mean acknowledging gaps we didn't realize were there. Science advances not by clinging to certainty, but by confronting anomalies honestly.